Hey everyone, so we've decided to start a bit earlier. We have Jan, the CTO and co-founder of Anjuna. He'll be doing a talk on secure enclaves for blockchain applications. And I'll let him take it from here. Can you guys just confirm in the chat you can hear?
Hey everyone, can everybody hear me? Hi, can everybody hear me? Yeah, sounds like, okay, sounds like people can hear me. And can everybody see my presentation?
Yep.
Awesome, okay. All right, just 1 second. Okay. Okay, awesome. All right, so thank you for attending and hope everybody staying safe during those times. Yeah, I'm Jan Chalewski. I'm the CTO and co-founder of Anjuna. We're an enterprise security company, and I'll be talking today about the uses of secure enclaves for blockchain applications and cryptocurrencies, and also giving a brief survey of the different use cases and the different concerns they can help address, and talking a bit about what we as the company do in the space and what solutions we provide. Just a little bit before I go into the kind of use cases and technologies, one sentence about the company. So the company was started early 2018 by my partner and CEO Eyal Yogev and myself. We're lucky to have several very kind of known advisors, including Professor Dan Bonnet from Stanford University, who obviously does a lot of work in the blockchain space and cryptocurrencies. Matt Pauker, whose company was acquired by Coinbase and who co-founded Voltage before that. And we're working with different industry partners and are likely to be backed by investors like Protocol Labs that are active in the blockchain space. So that's a little bit about us. So just to start, and I'll just open the questions. I see if anything comes up. Just to kind of start, I'd like to talk a bit about the different challenges, both in the blockchain protocols and also in the infrastructure that's related to running blockchains and cryptocurrencies. So some of the challenges around the protocols themselves, sort of the schemes for implementing blockchains and cryptocurrencies, are related to the fact that distributed ledgers that solely rely on distributed consensus and proof of work incur high operational costs. And that essentially drives up transaction fees and can drive latency up. And also create some problems around amassing dedicated ASICs, and sort of whoever can do that starts controlling mining, which hinders true decentralization. Some protocols also require a trusted setup. So while we're sort of trying to kind of get rid of trust that's not based on the protocols and on the technology itself, we're relying on this initial step. And that creates some debates around kind of whether the setups can be trusted. Well, obviously, some protocols are kind of providing solutions to that. There are also issues that are related to privacy around the transactions that are occurring on the blockchain. So there are some cryptographic techniques that are required for privacy with things like zk snarks addressing certain concerns. First of all, I guess there are all kind of concerns around the complexity of those and the state of research, and also kind of being very forward-looking things like quantum resilience come into play, and there are questions around kind of whether those techniques would be secure when we have quantum computers around. There are obviously new solutions like Starks that are providing that are addressing some of those things, but they still kind of run into some performance issues and are still kind of early in their development. And some of these can also create friction around rapid development of protocols. So when there's a lot of heavy cryptography that needs to go into that, it obviously kind of requires focusing on that and create some friction around kind of thinking about the business logic that you might want to focus on rather than kind of on the technicalities of how do you achieve trust and achieve consensus over what's happening on the blockchain. There are some infrastructural challenges as well, and those include things like secure storage of cryptographic keys and authentication credentials. Essentially, all of or many of the protocols sort of take for granted that you can securely store the keys to your assets, which is...
Hey, Jan, are you still on the
yes.
first slide? Because it shows you're stuck there.
Oh, sorry, that's kind of weird. Yeah, I see. No, I'm not on the first slide.
All right, let's maybe close out your video and start again.
Okay, yeah, let me share it again. Can you see that?
Yes. Do you want to try switching slides?
Yep. Can you see the slide switching?
No.
That's super weird. Let me try one thing.
Cool.
Let me share the whole screen, maybe.
Yes.
Can you see that? Can you see the slide
Perfect.
switching? Okay, awesome. All right, so getting back to the slide. One concern they mentioned is the secure storage of cryptographic keys and credentials. That relates to also sort of the general security of custodial services if you're using those for storing keys to your assets. Some solutions rely on hardware security models, and this is kind of the traditional solution for storing keys, but that can quickly become very expensive, and it's not a very flexible solution necessarily if you're sort of trying to rapidly develop the system and switch between schemes, scale it. You quickly run into problems with that. And I guess the more general kind of issue of infrastructure security of crypto exchanges, which sort of creates an unprecedented opportunity for attackers to get access to something valuable, and obviously requires sort of new solutions for really securing this infrastructure. Secure enclaves is essentially a hardware-based security technology that started being introduced into server-grade processors around 2015, kind of with Intel shipping Xeon servers to the market and AMD coming up with the EPYC server. And there are a couple of different technologies, but essentially it boils down to having some sort of a key fused into the CPU. And the new architecture provides the ability to encrypt memory, encrypt whatever goes from the CPU cache into memory, into the DRAM, and isolate the access to this data whenever it's in the CPU itself from any other process, from any other enclave. And there's also an attestation capability, which enables an enclave to prove to a remote party, such as a client that's communicating with the enclave, that it's indeed a secure enclave built on some technology you trust, and not just an attacker trying to spoof that. So if we're looking to kind of the new attack surface that it provides, it essentially looks like this diagram. So on the left, we have the attack surface without enclaves, and that includes obviously the whole application, but it also includes a potentially vulnerable operating system with frequently disclose the exploits. It includes the hypervisor, the virtual machine manager, and it can also, this diagram actually doesn't include it, but it can actually include the hardware, something like untrusted hardware parts, and that creates concerns around the supply chain itself. And with Enclaves, you can get potentially something way better, where the application can create a secure region that's running some protected code that accesses some protected data, and then a bunch of this attack surface goes away with no need to rely on the operating system anymore to enforce security and privacy, no need to rely or trust the hypervisor, and even many aspects of the hardware. So you essentially can boil down your trust to the CPU manufacturer itself. And those technologies are, to some extent, becoming an industry standard, with many of the public clouds adopting those technologies. They're making somewhat different choices around them, some going with Intel, some announcing support for AMD, some developing their own technologies like AWS Nitro. We see support in all the major hypervisors around this technology. And we see that all the known security chips support enclaves or trusted execution environments more broadly in some form. So Intel is, I would say, probably leading the space with Intel SGX, and AMD focused on AMD SCV for kind of full encrypted VMs, and ARM for a long time had the ARM Trust Zone. So those are some of the different enclave technologies, and there are also some that are open source, like interesting projects that are building secure enclaves into RISC-V, like the Keystone project. And so with time, I hope to see support for secure enclaves on different platforms. Let's talk about a couple of applications of secure enclaves in blockchain. And I'll go just over a couple of examples, but it barely covers all the different applications and the different uses that people came up with. There are so many publications around that, so much academic research around how to use enclaves and trusted execution environments in general for as different building blocks in the blockchain. So it can potentially be a critical building block of the protocol. Just to throw in some examples, and I have dedicated slides to explore a couple of those use cases. T-Chain is a blockchain protocol that uses a trusted execution environment to sort of secure transactions instead of sort of relying on waiting for a broad consensus. Poet is another one that uses what's called the proof of elapsed time. There's a proof of luck protocol that's relying on an enclave executing a certain operation and coming up with a proof of sort of being lucky, kind of solving some puzzle successfully. And Ekiden is an example from the smart contracts domain, where enclaves are used for ensuring the privacy of the execution of the smart contract within the trusted execution environment. There's also this whole use case of trusted oracles for smart contracts. So smart contracts execute on blockchain, but they're kind of disconnected from the real world, in the sense that they can execute sort of pure logic, but they're not connected to external services, which can be all kind of things. It can be all kind of web services that provide some data. For instance, if you want to execute some trading on a smart contract, maybe you want access to some trading data that's of the chain that's provided by external services, or things like trusted time that you might need for execution of some contracts. So there are all kind of solutions that are relying on that, such as Town Crier, and they rely essentially on trusted execution environments to provide this building block, to provide this oracle that's external to the contract itself. There are sort of the more straightforward use cases around key management and storing keys. where you essentially use those enclaves to secure your most valuable assets, which is the key that enables you to do transactions. Or sometimes it's keys for other uses, such as, for instance, validator keys that are signing blocks or transactions in different protocols. There's one use case on which we have our own blog post, and we posted that after we enabled running a full Tendermint node in an enclave. Tendermint is a project that implements Byzantine fault-tolerant consensus protocol. So for Byzantine fault tolerance, you're essentially running many nodes, and you need to ensure that not more than a third of those nodes are compromised. So that can be fine with many, many nodes, but when you're bootstrapping the network, potentially you have a small amount of nodes, and it's not so hard to compromise more than a third of them. And that's something where secure enclaves can come in and provide this additional protection that makes it way, way harder for an attacker to compromise a node in such a network. Can everybody see the slide? Yeah, I'm just making sure that you see my slides while I switch. Okay. Yeah, so another way I'm thinking about it is that this technology enables to maintain sort of what I call the security equilibrium. So kind of looking at the left end of this graph, kind of top left, we can maintain security equilibrium by, actually, I'll start from the bottom right. If we're using regular nodes that are not very well protected or are not utilizing hardware-based security to protect the execution, we might need a large amount of nodes. We might need a very kind of large consensus to make sure that our scheme, our protocol is not compromised. Essentially, kind of replicating the execution over many nodes to ensure that an attacker, it's hard for an attacker to compromise a substantial amount of those nodes and breach the consensus. But we can potentially start decreasing the amount of those nodes and maybe drive down operational costs or just kind of the total cost of ownership of the infrastructure related to running this network. And we can decrease the amount of nodes while maintaining the same level of security by introducing hardware-based security. Essentially, every node runs the protocol inside an enclave, and that makes it way harder to compromise a particular single node or a large amount of nodes. So sort of kind of the other extreme is running on a very, very secure hardware with a small amount of nodes. So that's another way to think of it, and it's kind of like this Pareto equilibrium. I want to go over a couple of case studies that illustrate those points. So one case study is the POET protocol that's been introduced in Hyperledger as a part of the Hyperledger Sawtooth blockchain platform. So that's essentially a proof of elapsed time. You have a trusted execution environment that is able to prove that it ran something for a certain amount of time. A certain amount of time has elapsed, and that's how sort of like a temporary leader is elected in this protocol. So that's something that you achieve with running inside the secure enclave called the Intel SGX, Intel Software Guard extension, that can attest to the correctness of its execution, and it has this access to a monotonic counter that can be trusted within the enclave, and that is incremented, and the result of it cannot be spoofed. And then the enclave provides an attestation to the result of this execution that can be checked by anybody else to ensure the correct execution of this protocol. So that's one example. If we kind of look at this example and compare it to different alternatives. And that's some nice table I found on the init3c org website. So if we look at something like Bitcoin, it's scalable. It's not necessarily very time efficient or energy efficient, and it has this problem with the ASICs and dedicated hardware for mining. And then we have those alternatives. For instance, an SGX proof of work would be ASIC resistant because that relies on a specific hardware. And if you trust that, and that's a separate question, then you cannot spoof the result of this execution with a dedicated ASIC. But it doesn't solve on its own the other two problems of energy efficiency and time efficiency. Something like a proof of time can solve energy efficiency because this proof of time doesn't require solving a hard puzzle, but it's not necessarily time efficient. You're essentially waiting for a certain amount of time to elapse before you're kind of signing off the transactions, the blocks. The other thing you can produce here is a proof of ownership, and that's related to the fact that this attestation that comes with Enclaves essentially guarantees to somebody who's validating it that you own a certain piece of hardware. You own this one processor that can be trusted, and it can provide a proof for that. So sort of you can rely on that instead of for achieving a consensus, instead of things like solving a hard puzzle or waiting a certain amount of time. So you just kind of provide a quote and you sort of cast your vote on a certain transaction, and that can be enough in certain protocols to sort of drive the acceptance of transactions. So yeah, so I think it's a nice presentation of the different trade-offs. Is it very scalable, this proof of ownership? No. Essentially, kind of rely on purchasing certain hardware for that. Another case study is using Enclaves, and that's by Lynn, Noor, Eyal, Kelbert, Gunsur, and Piazov. And that's related to the use of Enclaves to sort of manage funds before they kind of go onto the sort of before they fully committed to the blockchain, kind of acting as a trusted treasury. So that's a problem that without Enclaves, something like the Bitcoin network was trying to solve through the use. I see there are some questions coming up, but yeah, I'll address them after I go over the slides. So that's something that was the Bitcoin network was trying to address through the use of something like the Lightning Network that enables off-chain transactions while in the meantime you're waiting for all of that to be committed to the blockchain. But the problem is there you don't have those quite the same guarantees that you get when your transaction is actually included in the block, and that's something that the teaching protocol is trying to solve with trusted execution environments. Slightly different example is Equiden. So I mentioned it before, but diving into it a bit, it's essentially a platform for trusted execution of smart contracts that also provides confidentiality and privacy. So the contracts themselves can be executed in this contract T, this contract trusted execution environment, and then can be committed to an append-only log. So what the trusted execution environment provides in this case is the ability to sort of operate and process transactions in an encrypted form, essentially taking the inputs, decrypting them, doing the computation and providing output in encrypted output. So that can provide confidentiality and privacy guarantees around sort of what happened in this transaction. So that just kind of the tip of the iceberg in terms of use cases. And I just gave a few examples. But I want to talk a bit about the obstacles to the adoption of secure enclaves. So first of all, it can be a bit time consuming. It's a pretty low level technology, and the details around that are slightly different across different platforms, across different processors, there are different SDKs that require you to put quite a bit of engineering effort to implement your enclaves, implement the interfaces between your software and the enclave, and implement this kind of trusted boundary within which you perform the computation. And that can also be, can quickly turn to be expensive. And also getting security right is not trivial. So there are multiple attestation schemes, different platforms. There are different security advisories that are coming up when there is some new research around the kind of vulnerabilities that are disclosed around that, and kind of microcode updates that the vendors ship. So being on top of that is not trivial. And also, more conceptually, drawing the right security boundary can be challenging. So the initial model with some of the secure enclaves, especially with Intel SGX, was that you have an application and you would create a small enclave within the application to protect some particular logic. For instance, kind of just taking a toy use case, you would take something like a web service that, say, signs something or authenticates, or say a web server that terminates something like a TLS connection, and you would put the key inside a secure enclave. So the key might be indeed protected by the enclave, but the application itself sort of has access to the untrusted application itself, where the attacker can still inject code, essentially can use this enclave as a cryptographic oracle. And it's not clear that it really provides the security guarantees you'd like. So that's another obstacle. And that's where we as a company come in and enable what we call the lift and shift approach for taking a whole application, a whole process, and running it within an enclave with very minimal effort. So we essentially provide a cross-platform solution that supports different hardware technologies, different clouds, and types of attestation. And we support all the kind of widely used runtimes and languages. And essentially, what we provide is this kind of wrapper or loader for an application that takes care of all the interaction of the application with the operating system, and can also, on top of the memory encryption itself that the enclave provides, it also protects storage by seamlessly encrypting the data that and the I/O that leaves the application, and it can also protect network connections in cases where the application is not taking care of it on its own, which means it doesn't terminate TLS on its own. In terms of support for different languages, we support things like compiled applications written in C or C++, Golang, Rust. We support some scripted languages like Python, Ruby. Also can run WebAssembly machines, Node.js programs, and even some more obscure stuff like Erlang. And we've recently added support for Java applications. Just to mention some examples of applications, and then I'll leave some time for questions. So we support different applications within the secrets management space for storing and protecting secrets. Service mesh components like HashiCorp Console Connect, Nginx, proxies. We support running entire databases inside enclaves, and that's where we partnered with the Redis Labs to protect Redis open source and Redis Enterprise. And we're also capable of running other databases. The interesting thing, I guess, to mention here is some applications that are particularly related to blockchain consensus. And one notable example is our ability to run an entire Tendermint node. So essentially a full validator or full node that participates in the Tendermint consensus, and just kind of running it seamlessly without any changes to the binary. With that, I'll quickly skip the demo because I'd like to leave some room for questions. So, yep. Yeah, so we have some time for questions from the crowd. So I see some questions about many nodes. Would nodes all share the same private key? If so, how can security of private key be ensured? If not, then for many nodes, does prover have to supply the same symmetric key to each asymmetrical key on each node? Yeah, that's a good question. I can go into detail on that, but essentially there are different ways, and that really can depend on the protocols. We encountered some use cases when we were asked about the ability to store and secure the same key for many nodes, and that's something that's possible using kind of key provisioning, where you can take an attested public key that was produced and attested by an enclave, and you can deploy an encryption key or a signing key to the enclave, to the different enclaves on different nodes. In this way, essentially scale this access to the same key. But sometimes it's okay to just have different keys on different nodes. For instance, if you're sort of trying to get like a wide enclave consensus where you're just checking that many different enclaves or many different nodes signed a certain statement or transaction. Any other questions?
Cool. If there are any last questions, if you guys can just drop in the chat, it'd be appreciated. Jan, do you have any final thoughts you want to share with the audience?
Yeah, I guess one thing. Yeah, I just wanted to mention. Feel free to reach out, and let me just share the. Feel free to reach out with the questions, and happy to kind of assist in any brainstorming around the uses of that, either to my email, Anjuna or the info. One thing I guess that I'd like to be clear about, sort of, it's not kind of sort of the one true bulletproof solution to everything, and it's important to understand that a combination of cryptographic techniques and enclaves is sort of probably the right way to go for many protocols, where it's something like a building block that helps you kind of iterate faster, explore different use cases, yeah. So there's a lot of kind of interesting research on the combination of the two.
Cool. So I think one last question came in. Mm-hmm. It was, do you have a doc on the multi-node signing scheme?
Sure. We have some material on kind of different key provisioning schemes. What I suggest is to maybe reach out with a more specific question, kind of elaborate a bit more on what you're looking to solve, because that's where kind of the solution engineering comes in. We have some general doc, but it might not address the particular scenario that you're looking into, and I'm happy to kind of help think through that scenario.
Okay, fantastic. This was a really great talk. Thanks so much
for
taking the time. All right, bye.
Thanks for organizing. Thanks everyone for joining.